This part of our review going into Calculus 2 is just a review of the concept of integration, and then a little bit about how we actually evaluate integrals. This will be our starting point in Calc 2, but the important thing to show up knowing is the way to think about integrals in a couple of different perspectives. So this is the standard integration problem that we often start with, which is finding the area between a curve and the x-axis. And so I have a region that's shown here in gray is the region below the curve y equals square root of x, and the x-axis between the value of x equals 1 and x equals 4. So I guess x equals 1 is here. So if we knew nothing about calculus, we could still come up with a ballpark answer for this by trying to estimate the area under the curve using shapes that we do know area formulas for. It may not be particularly intuitive that we would use rectangles under something that's sort of slanty like this, but if you remember how this was introduced in Calculus 1, then you'll see, then you know ahead of time why this makes sense. So we'll go with that. So what I've done here is I've divided the region into 6 strips, and each of these strips I've capped off with a horizontal top so that I have a rectangular shape. So to find the area of the 6 rectangles, what I need to know is the height times the height and the base of each one. By making the strips equal width, I know that the width of each strip is the same, so I can just take the total width of the picture, which is 3 units across here, and I know that if I cut that into 6 strips, that means each of them has to be 1/2 unit wide. So each of the 6 rectangles has a width of 1/2. So that's half the battle, trying to find the area of rectangles. The other thing I need to know is the height of the rectangles. So the height, in this particular drawing, I've drawn them so that the top of the rectangle touches the curve on the left-hand side. And so we often call these left rectangles. That's what this notation up here is. I say L6. I'm shorthanding 6 left rectangles. So a left rectangle means that the top of the rectangle touches the curve on its left side. And the height of each rectangle, so the height of this first rectangle, is just going to come from the y-coordinate of that point. The y-coordinate of a point on a curve is found by just plugging the x-coordinate into the formula for the curve. So because this leftmost point is above x equals 1, then the height, I'll just write the coordinates. The coordinates of that point are 1 comma square root of 1, and so the height of that rectangle is square root of 1. Now I know square root of 1 is 1, but I'm going to write it as square root of 1 for now, just so that we can kind of see the pattern as we work our way up along these other points. So I'm going to jump to the last point. The last point has coordinates. Well, I need to know the x-coordinate. The x-coordinate is here, and so remember, all my widths are 1/2, so the x-coordinate here is 3.5, and the y-coordinate, again, because that point is on the blue curve, the y-coordinate is just the square root of 3.5. To find my y-coordinate, I'm always just plugging my x-coordinate into this formula. So all of the heights of the rectangles in between can be found by using the square root of the corresponding x-coordinate. And so now I can find the sum of those 6 rectangles pretty simply by taking the height of the rectangle times the width, height times width, height times width. Notice the width is always 0.5, and the height is always coming from a y-coordinate, meaning it's coming from the square root of something. And if I add those up on my calculator, I get as a value about 4.41. Now I can see from the picture that that's too small. Those rectangles are all sitting underneath the original gray region, and so I know 4.41 is a lower bound on the real answer. In other words, it's a number that's definitely smaller than the real answer. If I were to, oh, sorry, there's notation. The notation that we use for this, which you may remember from Calc 1, and that's important, is this idea of using a sigma. So the sigma, remember, is referring to summing things. The y-coordinate in each case is coming from plugging an x-coordinate into the function, in this case the square root of x. So x sub k here is just referring to the various x values that I'm using. So when I draw my strip, I have x1 is at the bottom of the first strip, x2, and so on. So this is x6. So if I refer to the positions of those edges of the rectangles as x1 through x6, then f of x1 through f of x6 are the y-coordinates. Each of those is multiplied by the width of the rectangle, and traditionally in math land, delta x is the change in x, and that's exactly what the widths of these strips are representing. It's a change in the x-coordinates along the bottom. So we think of f of xk as being the y-coordinate of the side of the rectangle that determines the height, and delta x is the width of the rectangle. And in our case, we've cut these into equal strips, so the delta x's are always the same, and so we don't have to play around with that. If you remember some more advanced ideas from Riemann sums, you know that it doesn't necessarily have to be the case that the rectangles are the same thickness, but if we're the ones cutting them, then why wouldn't we make that as easy as possible? So that's what the notation looks like for Riemann sums, and yeah, and in this case, these are the left. If I were doing the same calculation using the right sums, the right rectangles, then all that means is that my heights of the rectangles are going to be determined by where the rectangle touches the curve on the right-hand side. And so notice that all those rectangles, the height of the rectangle is determined by where the rectangle touches the curve on the right. Those points are still on the function y equals square root of x, still on that graph, and so they're all still going to be the square root of something. The widths of those rectangles are all still 1/2. So each one of those rectangles is going to have an area that's the square root of the x-coordinate it's sitting over times 0.5 times its width. And so this sum looks very much like the same kind of thing. In this case, the sum evaluates to 4.91, and I can see these rectangles are all above the curve, and so the sum of those 6 rectangles are going to be bigger than this gray area. So 4.91 is definitely bigger. It's an upper bound on the real answer. And so now between the two things, we have it kind of narrowed down that we know that the real gray area is somewhere between 4.41 and 4.91. Definitely sure that the real answer is somewhere in that range. Writing this with a Riemann sum, notice it looks exactly the same as the other one. The only thing that makes this different than the other calculation is that in this calculation, these are the x-coordinates that I'm using. I'm using the x-coordinates that are sitting below the right sides of the rectangles instead of the left sides of the rectangles. So by having slightly different values of x that I'm putting in, I really do have a formula that looks exactly like the other one. So we're starting to get the idea that this is a sort of a fundamental structure about approximating areas, and that the flexibility we have is sort of how we pick those x's. And that's exactly what happens with Riemann sums. So like I said, we can see from the picture that the left rectangles are too small and the right rectangles are too big, and so that means the true area is somewhere in between. Let me change color. So these are less than, and so that helps us narrow it down. This would be true regardless of how many rectangles we used. Left rectangles, no matter how many of them there are, would be too small, and right rectangles, in this case, will always be too big. And so it really is not so much how many rectangles you have as the fact that they're left or right that gives us this relationship. So if I were to draw 30 rectangles, it's a little hard to look at, it's hard to see in the picture, but the left rectangles, the sum of 30 left rectangles is smaller than the real area, and the sum of 30 right rectangles is bigger than the real area. What I've done here is I've asked a computer to calculate the sum of the 30 left rectangles and 30 right rectangles, but the process would be exactly the way that we saw in the example with 6. Notice that the left rectangles and right rectangles are getting closer to each other. There's less of a gap here between them, and so it starts to be more meaningful that we know that the real area is in between these two. That's a lot more useful to know the areas between 4.6 and 4.7 than it is to know the areas between 4.4 and 4.9, like we had before. And so there's no reason to stop with 30. We could go on to 300. I didn't make the picture with 300. It's really hard to see what's going on. So this is still the picture with 30 rectangles. But it would still be true that the 300 left rectangles and 300 right rectangles are still have this relationship that A is in between them, and a computer would tell us that these are the two values. And so now we actually get a very good idea of what A is. It's somewhere between 4.66 and 4.67. So we're really narrowing it down quite a lot. And all we need is a computer that can add up areas of rectangles, which is not a particularly hard arithmetic operation. Let's get, no. We thought the answer was in between. Oh, I didn't realize I did 3,000 rectangles. That's a lot. Anyway, but our work with the rectangles, we had narrowed down that A was in that ballpark, and then now the other way you may have learned to do this, other than breaking it up and approximating it, is with what's called the fundamental theorem of calculus. And so I want to make sure we remind you of that real quick. If I were doing this, the nice thing about the fundamental theorem of calculus is that it will give us the exact answer. The downside is that it requires that we figure something out that may not be that easy to figure out. So here's how I said that the fundamental theorem of calculus says this, that we can figure out the integral of a derivative function very easily by just plugging in the endpoints of the integral into the original function. So that can only help us in this problem if we can find a function that has as its derivative the square root of x. And so when we can do this, we sometimes say f of x is an antiderivative of the square root of x. That's what our goal is. Find a function whose derivative is the square root of x is the same thing as saying find an antiderivative of the square root of x. So I need to find an antiderivative of the square root of x, and then I can just plug in the numbers 1 and 4 and subtract, and that will give me the exact answer. So this may seem like this is not a big deal because our experience in Calculus 1 is generally only trying to do this for very simple functions. But in fact, this is a really, really hard thing to do. Finding an antiderivative of a function is not simple, and in fact, it may not even exist in terms of simple elementary functions. And we'll see that in our Calculus 2 course. We'll see lots of examples of functions that just simply do not have a simple to state antiderivative. And that's a real limitation on this particular way of thinking about the fundamental theorem of calculus. This tells. In this case, it's not too hard to do. This is an antiderivative of the square root of x. It's easy to check. If you take the derivative of the thing I just put in green, it becomes x to the 1/2, which is the square root of x. So because that's an antiderivative, I can now proceed with the fundamental theorem of calculus. This is the derivative of f, and so the answer to this, our integral problem is just the value of f of 4 minus f of 1, so we can plug in 4 and 1 and subtract, and we get 4/3, which it won't be that surprising to know that's 4 2/3, which is 4.66666, and so on. So remember that's exactly what you get is 4 2/3. And so yeah, it does sit between 4.66 and 4.67, and that's not a coincidence. So that's how the fundamental theorem of calculus works. On first day of class, we're going to work through a little bit of we're going to do a little bit of work to try to understand why the fundamental theorem of calculus works in some very simple cases, and then we'll get on with kind of reviewing the very end of Calculus 1 so we can get started with the Calculus 2 content still during our first week.